So today I want to talk about how you get one theory out of another, and with some type of operations. Sometimes they're called modular operations, S and T. So with this operation, we'll be able to go from one theory to another and from one duality to another. And also I'll introduce notations that quite significantly simplify many of the previous notations. Okay, so let's begin. So let's say start from a critical theory. Let's just say we start from some CFT. Right? Pick your favorite, Wilson-Fisher, free fermion, doesn't matter. The only thing you really need is that this CFT has a anomaly-free U1 global symmetry. All right. So let's denote the partition function of this guy as Z. Let's call it CFT1. And since you have the U1 symmetry, we can put in a probe gauge field, capital A, to it. Since I assume that is anomaly free, this partition function as a functional of the probe U1 gauge field is perfectly gauge invariant. So now we define the S operation. Essentially by making this capital A dynamical. Okay. So the new partition function, which I call the S of CFT1, okay, it will be also a functional of another probe U1 gauge field B, and it's defined as the further path integral over my original probe gauge field, capital A, CFT1 as a function of A, with the additional BF coupling. Okay. This kind of BF coupling was mentioned quite a few times in yesterday's lectures. Okay, so essentially what I do is make a promote A from a background gauge field to a dynamical gauge field, which is legal because I've assumed that my original theory has a non-anomalous U1 symmetry, and then further I demand this U1 gauge field has a flux conservation symmetry, so that there's an additional U1 symmetry coming out of it, which I probe with this capital B. Yes. Yeah. I'll comment that about that right now. Okay. But let me first just summarize what I have said so far. This is another CFT. Let's call it just S on the original CFT with a U1 global symmetry, with another global U1 probed by this by this B. Okay. So now let me comment on this other point, which was the question raised just now. That is the definition above formally gives something that's conformally invariant. So it's formally conformal. But just like any other path integral, you can always legitimately ask, is it even well defined? Right. The point is, if you want to make sure it's really defined as a continuum field theory, the safest way we know how to do that is to define it as a renormalizable through a renormalizable Lagrangian, which means, so if we want to define it as a renormalizable field theory, we should define it starting with a kinetic term for the dynamical gauge field. So we need to put back in the Maxwell term, which let me write it as the SCFT1, but with a coupling E square, right? Which is basically everything up there, but with the additional Maxwell term. So I have this BF coupling, and the Maxwell term. Okay. So this is perfectly well defined, except it's no longer guaranteed to be conformal, right? I mean, the Maxwell term is not conformal. So we lose conformality as a price. So it's not conformal unless we take the limit of E squared going to infinity. Which tells you that this S operation truly gives you another good CFT only if this limit exists. Okay, so so the S gives another CFT if this limit exists. And that's not always the case, turns out, which is not a priori guaranteed. And in fact, we have discussed a counterexample of this yesterday. Let's say you start from the free boson, the Gaussian theory. You couple to a Maxwell U1 gauge theory. The theory is unstable. It flows to some first order stuff. And because there, so let's say just take this theory plus a Maxwell coupling, it's unstable, and the instability happens basically as your energy scale goes below E squared, right? So there's instability as your energy scale, let's say E, let's use mu, approaches E squared. So now if you try to take the E squared going to infinity limit, that's basically saying you're always unstable, right? It doesn't matter where your energy scale is. It doesn't look like a CFT. It doesn't look like anything. I mean, we know it's a first order transition, right? So, so that's a warning that, sorry, the energy scale, yeah. So, so this is a warning that this may not always give you a nice thing. And in fact, there are even more subtle examples where this limit does exist, but it doesn't commute with some other limit you want to take in the theory and so on. So this is a warning. However, we'll proceed without worrying about this subtlety. Essentially, this counterexamples do exist, but as far as we can see, they don't appear that often. So we'll proceed. Just without further worrying about it. And if anything goes wrong, we'll come back and revisit. You know, I don't feel too guilty about saying that as a physicist. Right. Okay. So that's the side comment. Yeah. So from now on, I'll just proceed, assuming that the limit exists and it also commutes with whatever other limit I want to take. Okay. Yes. No. The thing. Oh, okay. The question is, does the limit give you a nice theory, right? For example, that theory, if you try to take the limit, it doesn't give you. I mean, yeah. It's actually not. It will flow. Yeah. Just, you know, just like you take any whatever Fisher or Dirac coupled to a Maxwell theory, it will flow. Right? It's not a fixed point. Right. So here, when I write down a CFT partition function, formally is already at the fixed point. Right. And if I further couple with this, the conformal symmetry is manifest. So it's formally a fixed point, except that fixed point may not be well defined. Right. So, but if I put in this Maxwell term, the theory becomes well defined, but it's not a fixed point. Right. And then you have to reach the fixed point, you want to take the limit, but then there are issues. There are potential concerns. So that's another way to put it. Yeah. So the word conformal is just a shorthand term for saying you are at the fixed point.
Sorry. So what's the relation between the renormalizability and that kinetic term? So why, if I want a renormalizable theory, I have to have that Maxwell coupling?
Because once you put in this term, because this term is UV relevant, right? So once you put in this term, you know at least in the UV, the gauge fluctuation is weak. You get a Gaussian theory that couples to your original CFT, which is in principle visually defined. Sorry? Oh yeah. It will flow to whatever it flows to. Yeah.
So that means that I want a weakly coupled theory, at least at UV.
Yeah.
So if I don't have a weakly coupled theory at UV, is that a problem?
Well, it's not necessarily a problem. It's just we don't a priori we're not completely sure if this is well defined. Yeah. I mean, if I just literally give you this and ask you to actually integrate out capitally for me, it's not clear how you do that actually. All right. Yeah. So that's the S operation. Then there's another operation which is the T operation, which is much less subtle. It's comparable to compared to the S. This is pretty trivial. This is really just add a background Chern-Simons term. Right. So essentially, I take from I define T of my CFT. For this one, I don't even need it to be CFT, but let's just stick with it. CFT So I'm just adding a background Chern-Simons term to it. Right? If you like, stack another integer quantum Hall insulator in the UV. Okay. So with this notation, so now the boson vortex duality has a very simple compact expression. It's that if I have the Wilson-Fisher, the O2 Wilson-Fisher, it is the same as the S operation acting on itself. Right? Remember, if you really unfold everything, this is an O4 theory tuned to the critical point. This is another O4 theory tuned to the critical point. But when you have an S, it means that this Wilson-Fisher couples to a dynamical U1 gauge field, and the flux of this dynamical U1 gauge field is a global U1 symmetry. Okay, so yeah, let me just to be explicit in case you are not yet very familiar with the story. Right. So this is basically saying that. And as I said, from now on, I won't worry about adding Maxwell term, taking limits, which coupling is bigger in the UV. I won't worry about any of that from now on. I've explained all the subtleties. We know what we're doing, and we just proceed.
By second third, do you mean in the large charge limit?
What do you mean?
I mean as Wilson-Fisher.
Sorry, what do you mean a large charge limit?
E squared goes to infinity.
Oh yeah, so here, yeah, whenever I do that, there's an assumption that this limit exists. But of course, since I'm writing Wilson-Fisher here, it means that Wilson-Fisher quadratic coupling was sent to infinity before this guy. So so those aspects were taken care of. Yeah. So this is, if you prefer, this is just a way to hide all the nasty details into some short, nice-looking formula. Yeah, it's fine as long as you know what you're doing. Okay. And the Chern-Simons bosonization talked about yesterday, which, let me remind you, is the duality between the two-component Dirac fermion, a massless Dirac fermion, and the U1 Higgs transition, except with a Chern-Simons term and the mutual coupling. Right, it's that. So that becomes simply Dirac fermion is equal to ST of Wilson-Fisher, right? So you read the operation from right to left. So Wilson-Fisher, T means with a with a Chern-Simons term. S just means you make this gauge field dynamical and then couple, and then make the flux conserved. Right. So it's a pretty simple way to write down. Otherwise, pretty complicated formulas. Okay.
Is there any statement on like nilpotence of these operations? Like if you square it, you go back to.
That's exactly the next thing. So then you can ask, okay, as a set of operations, what kind of algebra does S and T give you? Right. So in fact, well, so algebra from S and T. Well, the immediate the pretty obvious thing is T is free, right? You can add transcendent term to whatever level, any integer, it will be a different thing. So T is free. And one can check that S to the fourth is 1. In fact, let me check that for you. So if I think square, the claim is that S square is charge conjugation. This I can do it, show it for you in real time. Square, let's say on on some CFT, probed again by this field B. If you just literally just copy that that expression here, it's something like dA2, my original CFT coupled to A2, and then there's the BF couplings, A1 dA2 plus A1 dB. Okay, so here notice that A1 doesn't talk to the original, the other dynamical degree of freedom. It only talks to A2 and B. So integrating out A1 is it just gives you a delta function, right? So now if you integrate out A1, it just sets A2 equal to minus B. Right, if you follow the plus signs, which means it just gives you my original CFT, but with minus, sorry, A2, yeah, minus B. So it basically giving back my original theory, except that my probe gauge field goes to minus itself. That's just charge conjugation. And of course, if you do charge conjugation twice, it's nothing. So S to the fourth is 1. Okay. And of course, because pretty much all the theories I talked about so far, like Dirac-Fermion or Wilson-Fisher, they naturally do have charge conjugation symmetry. So S square equal acting on them naturally gives back to the original theory. So sometimes I won't even distinguish S and S inverse that carefully, because and here's a more non-trivial one, which you can check on your own. I won't do it for you. I mean, it follows.
Sorry, I didn't get the last comment. How do you act with charge conjugation on other matter fields?
Oh, yeah. The statement is whether you have, let's say, you take your Wilson-Fisher boson. Charge conjugation just means phi goes to phi star. The theory is invariant. Right. Similarly with Dirac-Fermion, I mean, you may need to take care of the gamma matrices, but at the end of the day, the theory is invariant. So that's of course saying that S square acting on whether Dirac-Fermion or Wilson-Fisher just gives back to the original theory. There's not even an anomaly involved. So which means as far as this are concerned, S and S inverse are the same. All right, so yeah, so here's a slightly more non-trivial relation, but you can check it following very similar logic. It's not too different. Just the algebra is slightly more complicated. Yes, that's exactly what I'm going to say. If you are familiar with modular transform, two elements with these properties generate SL2Z. Okay, so these are 2 by 2 integer matrices with determinant 1. And in fact, if you represent this as 2 by 2 integer matrices with determinant 1, the S is represented by essentially the epsilon tensor, and T is basically I think this guy. Okay. So, yeah. Yeah.
Here I assume you put the theory in the flat space R3, but if you put the CFT on torus, is it still true that it's you act with x squared, then you get the relation dA1 equals dB, but then it's not obvious on torus that A2 is always equal to.
Oh, yeah.
0.
So that would be a legitimate worry if this level is some k larger than 1. It turns out at level 1 is fine. It doesn't give you anything wrong. Yeah. So, well, because as a TQFT, it's trivial. So that's why you can integrate things out without. But if you have level 2 and so on, there will be lines that are that can be 0 or pi, and you're neglecting that. That can potentially give you a problem.
Okay,
Yeah.
thanks.
Sorry. Where am I? Oh yeah. Okay. So this gives you a SL2Z, and actually you can consider one more thing, which again we kind of talked about quite a bit yesterday, which is time reversal symmetry. Right? It may or may not be a symmetry depending on what theory you have, but you can always consider the time reversal operation. Right? Let's think about time reversal, or any space-time orientation reversing operation. It can be space reflection. In fact, it doesn't really matter. So let me call it curly T. I hope it's obviously enough. That's not that T. You can complain if it doesn't. It's not obvious. Which is sending the gauge field to the 0 component is invariant, but the spatial component pick up a minus sign, and that's how normally you implement time reversal. If you have that, you can check that the algebra between time reversal and the SNT is such that whenever you try to commute the T with the time reversal with any of the element here, you get an inverse. It's something you can just check. So now, as I said, SNT generates SL2Z, and then you can ask, what now if you putting this time reversal, what does it generate? Well, so ST and time reversal generates what's called SL plus minus 2Z. So these are 2 by 2 integer matrices with determinant that's equal to plus minus 1. So essentially, time reversal acts like an improper reflection in this SL2Z space. Okay. So if you like, in that basis, time reversal looks like 1 minus 1, this poly Z. So it has funny structure. Maybe tomorrow or something, I'll give a much simpler interpretation of why these things appear. Turns out they have a very natural interpretation as the electromagnetic dualities in 3+1 dimensional U1 gauge theories. But for now, let's just stick with these operations. And of course, let me just remind you from yesterday that the Wilson-Fisher is manifestly time reversal invariant. So this is true. And the Dirac fermion is time reversal invariant up to an anomaly, right? So remember the Dirac fermion picks up a Chern-Simons term upon time reversal, but picking up a Chern-Simons term is just doing the T. So the compact notation is this. Okay. And let me just, illustrate to you the power of this kind of simple formal manipulation, which kind of make things more simpler in some sense. So let me remind you, from yesterday we had the the Chern-Simons bosonization. Which is the Dirac fermion is S and T of the Wilson-Fisher. And yesterday I spent quite a bit of time talking about how this duality can quite non-trivially be compatible with time reversal symmetry, right? So where the Wilson-Fisher boson goes to its vortex under time reversal. So we can check that with just this simple algebras. So under time reversal, let's just implement time reversal on both sides. So on the left-hand side, time reversal acting on D, as we just mentioned, is just the T. So on the right-hand side, well, time reversal acting on this S and T, well, we can commute it all the way in. So, but remember, every time we commute, we convert the S and T to S inverse and T inverse. And time reversal acting on Wilson-Fisher just gives you Wilson-Fisher. So it's this guy. But as I said, since S squared acts quite trivially on all these theories, let me not worry about the S inverse. It's just S. And then let's remember now use the boson vortex duality. Just rewrite this as ST inverse SWF, the Wilson-Fisher. Right? So I'm just using the Wilson-Fisher equal to S Wilson-Fisher. So now you get this guy. But by the SL2Z algebra, this guy to the cube is 1. That's just, we replace T by T inverse, nothing changes. Yes. Sorry? Sorry, where? ST2, this one?
Yeah, that should be minus identity. Shouldn't that be, or?
I mean, ST cube is 1. Sorry, so
-1.
oh, sorry, yeah. Yeah. Sorry. Yeah, I think that's the C. Yeah, I guess at some point when I was preparing, I sort of used the fact that S squared is kind of trivial, so -1 doesn't really do anything on this kind of theories. Yeah, so for now let's just do that. Yeah, I think I can correct the minus signs somewhere, but it's probably not unwise for me to try to do it in real time. Yeah. Yeah, let's just stick with this, and what you will find is that means the ST inverse S is equal to, just by expanding this, TST. So it's TST WF. So here you got this. So essentially time reversal acting on this guy is just this guy with the Chern-Simons level shift. So so without worrying about all those integrating out this gauge field, that gauge field, and so on. You just use the SL to Z algebra. It's all automatic. Okay. Of course, at any stage, if you are unhappy with the compact notation, you can always expand the whole thing with the proper gauge field to put it. Okay. So now with this equipped, yes.
What can you achieve? Because from t equal to t difference.
Sorry, from.
I mean, what can you achieve?
Oh no. So here I'm checking time reversal for you. I'm just showing you that time reversal can act on this and give you the same thing. It was like a consistency check. Yeah, because here I'm just using the Boson vortex duality without assuming the bosonization duality, right? So I mean, it essentially repeating what I did yesterday for the time reversal, but in this more compact notation, just to get you familiarized with this a little bit. Yeah. But of course, the real use of this S and T operators is that we can generate new dualities. From old ones. Essentially, starting from this bosonization duality, we can generate infinitely many more duality relations. So a simple one is, let's say we can take the inverse of this one, right? Since now, so for example, take the inverse of the bosonization. So D should be, well, take the inverse of that one. That gives me, sorry, the Wilson-Fisher should be ST inverse of D. Right, just moving this to this side. But of course, that's T inverse S inverse D. And then you can unpack it. Right? This is really just saying that this guy is dual to, well, the way you unpacked it is to read from right to left. So you have an S. So it means the gauge field is dynamical. Then you have a T, sorry. The gauge field is dynamical, and then you have a T inverse. It means you have a minus Chern-Simons term, right? So you can unpack things at any stage. Just read from right to left. Of course, you can also take the time reversal. By this time, by now, it's a relatively straightforward thing. Take time reversal. The Wilson-Fisher doesn't change. The other side, T inverse becomes T, S inverse becomes S, and time reversal acting on D gives you another T. This is another one. Of course, you can also unpack it. I'm not going to do it. Okay, so that's the inverse bosonization. Actually, let me keep this one. Yeah, I think I don't need this. No, actually. Okay. So equipped with this, you can generate many more things. But I'm going to spend some time on one particular duality that's relevant for example, the Harfield-Landau level problem. So So let me show you a fermion duality.
So
Yes.
here you're talking about the fixed points, the IR fixed points of these theories, right?
Yeah.
Okay.
Yeah.
Good.
Okay. Yeah, I mean, these two theories in the UV are manifestly different. So, yeah. So this one was first discussed by Boson and shortly after by a bunch of other people. So let's just start again with the bosonization. This is ST of the Wilson-Fisher. But then let me now use this one. Just paste and copy. So that's TSTD. But of course, this merges to this guy. Okay. So now you can unpack it, which is saying that the free Dirac fermion is allegedly dual to another Dirac fermion coupled to a dynamical gauge field. T means there's additional Chern-Simons shift. S means it's dynamical, of course. A, D, B. Another T squared just means you have a level 2 Chern-Simons term added. And the final S is just it's the old friend, just B, D, A. Right, so seems to be a long equation, but it's just unpacking this thing. So of course, you may be not, this side looks a little bit long. It's perfectly well defined, but it looks a little bit long. So it can be made nicer if you do something slightly fishy, slightly illegal. So let's do something slightly illegal just to make things look nicer. Right? So let's do something slightly illegal. There are two things. One is just write this Dirac fermion in a more conventional sense, which is as let's make the half-level Chern-Simons response manifest. It's fine as long as we know what we mean. So it's not really a big deal. And the second thing, which is a little bit more serious, is that let's integrate out this this little B gauge field. So this is a little bit problematic because you see that this is level 2 Chern-Simons theory, so it's a non-trivial topological quantum field theory, and integrating out such non-trivial TQFT. When doing that, you lose information on non-trivial manifold. For example, if you're on a torus or higher genus surface, you lose your ground state degeneracy. So it's a little bit more serious problem. But let's say, suppose what you care is local correlation functions and so on. It's not that a big deal. Okay, so if you do both of this, you get something that that looks really pretty. It's pretty enough that all this illegality is perhaps worth it. You get this. The Dirac fermion is dual to another Dirac fermion, but coupled to a dynamical gauge field. And that's it. Right. It's a much shorter equation. Looks much nicer. And you find that there's a good reason to write it this way, because immediately this reminds you of the boson vortex duality, right? Remember, the boson vortex duality looks something like for a Wilson-Fisher boson. If you gauge it, pretty much is the original theory, right? So this is, if you put these two together, it's obvious that this is really a fermionic generalization of the bosonic charge vortex duality. Yes. Sorry, this one. This one, I would say it's more like a redefinition of Dirac fermion anyway. So you're essentially choosing a slightly different regularization of the Dirac fermion. So that I'm less worried about that. Yeah, just essentially you just keep in mind that whenever you write down a Dirac fermion, you really mean this one with the half-level Chern-Simon term subtracted. But that's fine. Yes. Yeah. Yeah. No, it's not a proof per se of anything. Depending on where you start. I mean, there are two ways of viewing it, right? One way is to say, let me assume that bosonization duality is true. If I just assume that, then time reversal must work out. And turns out of that, I can derive the boson vortex duality. That's one way to view it, right? Which is fine. The other way, alternatively, you can say, I'm a little bit suspicious about the bosonization duality. And then, okay, the point that makes me, the most important point that makes me suspicious is how time reversal works out. And then want to make sense of it. And then you can say, okay, turns out time reversal can work out using the boson vortex duality. Either way works fine. I think which viewpoint you take largely depend on what background you come from, right? At least within condensed matter community, for a lot of us, the second view was more common, right? Because we have such strong faith on boson vortex duality. It's supported by numerics and all that. There's no one doubting about it. So being able to just rederive boson vortex duality doesn't seem a big deal. But showing that the bosonization makes sense is kind of important. Right? But if you come from a more field theory background where duality leading to emergent symmetry is pretty common, for example, in supersymmetric dualities, then the first point of view may be more natural for you. So, yeah. All right. So I think my next thing is to talk about how to apply that for the half-field lambda level, but I think this is a good place to pause. So that would be the afternoon. So, thanks.
Let's start again in 10 minutes.
Oh, yeah, okay.
Yeah, today we go straight and then we have lunch.
Yeah. All right, so I sense that this thing may be a little bit abstract. So let me do something pretty concrete for this lecture. Let's do quantum Hall. Nothing can be more concrete than that. So so let me think about something that looks really simple, except it's not. Let's think about starting from a Dirac fermion and putting it under a constant magnetic field. So so just this good old Dirac fermion, but turn on magnetic field. non-zero. Yeah, constant meaning constant in space-time. So of course, this is a free fermion problem. The Dirac equation is easy to solve if you turn on a constant B field in XY plane. You get lambda levels, basically. Important thing is the gap between the lambda levels are of order square root B. Okay, and each lambda level has some huge degeneracy. I think you get a degeneracy that's basically proportional to the total number of flux in your system. Right? Essentially, B times the total volume of your system, the L square, over 2 pi. Yeah. So it's essentially a huge degeneracy. And of course, turning a magnetic field on also breaks Lorentz invariance. So we are now pretty far away from the conformal regime. We're talking about something highly non-relativistic. Another thing I want to do is to impose the CT symmetry. It's an anti-unitary symmetry that looks like time reversal, except they also conjugate your U1 charge. Again, up to the anomaly. So this symmetry, what it does is to conjugate my charge. So psi goes to psi dagger. Of course, it's anti-unitary, so I goes to minus I, and the probe gauge field, the zero component flips sign, but the space component does not. And because the space component does not flip sign, so having a constant magnetic field is perfectly fine with this symmetry. Ordinary time reversal would not. And also because the Dirac fermion flips under it, the charge density of the Dirac fermion, as this guy, should be 0. Right? Of course, because of the anomaly, the actual charge, as defined as the variation with respect to the zero component of the gauge field, has an additional piece from essentially the parity anomaly, or from the polyvelar regulator, which is this guy. So it means that the total charge is B over 4 pi. Okay, so now with at least within free fermion, it's easy enough to figure out the ground state. Doesn't look super weird. Essentially, because you are at neutrality, right? As we require the total Dirac charge to charge density to vanish. If you're at neutrality, your ground state basically has all the negative. Sorry, I should have said this middle Landau level has energy exactly at 0, and the other guys have plus minus square root B. Right. So the ground state is basically you just make all these negative Landau levels filled, all these positive Landau levels empty, and because you are at neutrality, you half fill. You fill half of the Landau levels at the 0 energy. The only problem is this Landau level comes with a huge degeneracy that's proportional to the volume. So if you have n energy levels and you fill half of them combinatorically, there are exponentially many different ways you can do that. And within free fermion, since and kinetic energy is 0 at that point, all these different ways of filling the lambda level gives you exactly the same energy. So you get a huge, exponentially huge ground state degeneracy. So free fermion, exponential in volume ground state degeneracy. Of course, this means that once you turn on even a little bit of interaction, this degeneracy will be lifted. At least we expect the degeneracy to be lifted. You know, things like the fermion quartic terms and so on. So even though such terms are irrelevant at UV, right? We're talking about a two-dimensional 2+1D Dirac fermion, so these quartic terms are irrelevant. But once you flow to the IR, once you flow below the lambda level gap, the square root B, that standard RG flow for the Dirac fermion no longer applies, right? Because I have an explicit scale, and this formerly irrelevant provision becomes relevant again, and they actually control your IR physics. So not only they control the IR physics, it's actually an intrinsically strongly coupled problem because the kinetic term is by definition 0 at the lambda level. So the physics is fully defined by the interaction, which is typically hard. So it's a hard problem. It's hard in the sense that if you only stare at this problem, the only Hamiltonian is quartic, so it's not even clear how you start analyzing the problem. Typically, we make some mean field solution and analyze around that mean field solution. But if you literally stare at the Hamiltonian, it's not even clear what kind of mean field theory you come up with. You want to expand around. And in fact, this is exactly the kind of problem that people working in fractional quantum Hall effect faces on daily basis. And in fact, this is the fractional quantum Hall effect problem. So the precise statement is that if I have interaction then the Landau gap, turns out this problem is becomes completely equivalent actually to the Landau level problem in non-relativistic firm. In Schrodinger fermions. Because if I write down the two-dimensional Schrodinger equation under a constant magnetic field and solve for the Landau levels, and I look at the lowest Landau level, in fact, the Landau level wave functions look exactly identical to this 0 Landau level wave function. Right. So if I'm in a regime where the interaction strength is much smaller than the Landau gap, I can project to the single Landau level and the two problems to become literally identical. Which means this problem has been considered with considerable effort in the quantum Hall community. And in fact, since the early 90s, there has been a quite successful theory to this. So there's a classic approach using what's called the composite fermions. There is a kind of mean field theory with perturbations you can analyze by Halperin, Lee, and Reed. So in the community, it's usually called the HLR theory. The theory is called the composite fermi liquid. And it's by any standard, it's a very successful theory. It produced many predictions that match with what people have seen in experiment, with one unsatisfactory aspect, which is the CT symmetry, which is also there in non-relativistic fermions, at least in the limit of large Landau level gap. The symmetry is not manifest. So I won't explain to you exactly what HRR theory look like and so on. That takes probably at least another lecture. But just to emphasize that there's some unresolved issue with the good old approach, and we're going to do something that looks quite different. Okay, so the thing that we can do, which was first noticed by Damsong, is that we can use this duality to tackle that Landau level problem. So again, for analyzing this, well, because eventually, just as a spoiler alert, eventually we're going to end up with a highly gapless state with many local, non-trivial, fluctuating local degrees of freedom. So the topological aspect, to some extent, is secondary. So let's not worry about all this fishy business with integrating out some non-trivial TQFT and so on. And let's just stick with the simpler version of the duality for that purpose. Okay. Yes. So the problem I'm considering is this half-field Landau level with some quadratic fermion interaction. The thing is, or more specifically, what I end up showing you is that what I will end up showing you is how do you even make up a mean field approximation to this kind of problem, right? And starting from that, you can analyze further, and which I won't do. But the general problem with this kind of thing is a priori you don't even have a mean field solution. The mean field means taking interaction to 0, but once you go to that limit, you get exponential ground state degeneracy. You don't know what that means. So you need some different starting point. Okay, so let's take this theory and analyze it. In fact, let me put back the Chen-Simons term. Just to emphasize that this state has Hall conductance 1/2. It's not too much of a big deal. So just take theory, and there it looks like like an interacting gauge theory, but there are certain kinematic aspects that we can get quite easily. For example, if I vary with respect to the probe gauge field capital A, I conclude that my current is just from this term, it's just minus 1/4 pi star dA. And from this background term, I get this background charge. Okay. If I write the zeroth component, this is just minus 1/4 pi B minus 1/4 pi curl A. Of course, whenever I write down things like this, I'm neglecting higher order derivative terms that can naturally come from, let's say, Maxwell term and so on. But for now, let me not worry about those terms. Okay. But as I already mentioned here, the total charge is just the flux density divided by 4 pi, which then means that the little a has zero field strength on average. I mean, there will always be higher derivative corrections, but on average, if you like, the expectation value of this curl A is 0. So that's already a good news, because the main reason why the original problem is hard is because I'm talking about a lot of electrons moving under a strong magnetic field. That's a hard problem. But now I'm talking about a bunch of this chi fermions, admittedly interacting to some fluctuating gauge field, but now they move at least in zero magnetic field, which looks much simpler. Okay. And then I can further vary with respect to little a. Essentially, that's demanding gauging variance. Again, up to higher derivative terms, I get the current for this chi Dirac fermions. This guy. Well, that's just saying that the Dirac fermion should have a density that's given by 1/4 pi times b, which is not 0 by assumption. Right. So what do I get? Well, I get a bunch of fermions with finite density, but coupling to a gauge field that has on average 0 magnetic field strength. That looks like a much simpler problem. Right. So essentially, I have my Dirac fermion, which are the chi fermions. But now, what's different from the original theory is that I have a finite density. So at free fermion level, it looks like a Fermi surface, and now coupled to a dynamical gauge field, little a. So the natural mean field solution, probably the simplest mean field solution, is just a Fermi liquid, or something that looks like a Fermi liquid, meaning the chi forms a Fermi surface. Essentially, what you have in an ordinary metal. Right. That's also coupling to this fluctuating U1 gauge field. Okay. So at least at the mean field level, we have figured out what it does. Of course, starting from here, you can start asking how much does the fluctuating gauge field still matter? You can start to do Feynman diagram, and you can start to ask all the questions such as is your perturbation theory controlled and all that. That's an entire industry. It's still an ongoing effort in the field, but there are many problems still unresolved there. But at least I think the consensus is that at least this state is stable. Right? It's not going to collapse into some completely different fixed point under RG. So this theory is known as the Dirac composite Fermi liquid. Any questions so far? Yeah. So it's a highly gapless state. In fact, it's more gapless than a CFT because you have an entire Fermi surface, and you get a lot of essentially at every point on the Fermi surface you get some gapless degree of freedom. And in fact, this theory is very similar to the original HRR composite Fermi liquid theory of formulated in the early 90s. If you're familiar with that theory, for most features, you don't actually see the difference. So most features of this theory are similar to the good old HRR. But the CT symmetry is manifest so it does come with some non-trivial consequence that's not there in the good old HR. So there is at least one non-trivial consequence. I mean, there could be more, but they have to be figured out carefully, more carefully. Consequence. Sent. HR. So that is about the Dirac spin. Right, so so this chi fermion is naturally a spinner. It has a Dirac spin that's pointing in some direction. Sorry, yeah. Yeah, I think I can get rid of this one. And now you ask, what does CT symmetry? How exactly should CT symmetry act on this theory, right? Remember in the case of for the original probe U1 gauge field, you have the curl of A goes to just curl of A. That's your magnetic field. But because of this mutual BF coupling, this Chern-Simons coupling, it demands the little a to do opposite thing. So in fact, this condition alone is saying that on average, your magnetic field should vanish. It also means that the chi fermion should just go to itself. Right. So it's an anti-unitary symmetry that, although flipping the original global charge, it does not flip the gauge charge. Which means this acts just like ordinary time reversal symmetry on the chi fermion. Right. So essentially, you need chi under CT to go to chi, something times chi, not with the dagger. But for Dirac fermion, for two-component Dirac fermion, for a single flavor of two-component Dirac fermion in 2+1 dimension, what you can multiply in front of this guy is unique. It has to be I sigma y. It has to be an epsilon tensor, basically. Which means that CT symmetry square acting on chi should give you a minus sign. So if you write down a two-dimensional Dirac fermion, that's inevitably what you will get. What does that mean? Well, it means that if I have a Fermi surface made out of this chi fermions, right, chi Fermi surface. On this Fermi, at this point, my Dirac fermion, let's say, is pointing this way. I mean, it has to point in the opposite way. Right? Which means there's certain scattering. If I try to scatter a fermion from here to here, right, from KF to minus KF, I have to also flip the spin. But if my scattering process doesn't allow me to do that, sorry, if I'm not allowed to flip the spin for whatever reason, let's say time reversal symmetry or the city symmetry, then this kind of scattering will be forbidden. So essentially, this means certain scattering process is forbidden by CT. And that actually comes with a real consequence, which is if I measure some local operator at momentum q, right, so let me right here, and if this operator is particle hole symmetric, is CT invariant, so this will be smooth as q approaches 2kF. So this is not there in the ordinary Fermi liquid. So if I have ordinarily, if I have a Fermi surface and I measure, for example, the density correlation function of my fermions, there will be singularities as this momentum approaches 2kF. It turns out to be pretty weak singularity, some log, but it's still singular enough that a numerics can see it without too much difficulty. Right? Leads you to various well-known effects in solid-state physics, such as RKKY interaction and Friedel oscillation. But if this and those singularities come from the fact that you can scatter from kF to minus kF. So when your momentum approaches 2kF, there's some funny thing that happens. However, with the particle hole symmetry imposed, this scattering is not allowed, and as a consequence, the correlation function behaves smoothly. And this has been numerically observed, right? So so this was numerically observed. So the reference is Goretz et al. So that's a strong sign that that this funny Dirac composite Fermi liquid is there in the hot field Landau level. Okay, question? Yes. Yeah, the thing is you have scatter from here. That's 2kF. From kF to minus kF. So the momentum difference is 2kF. Yeah. Well, essentially the idea is if you are the 2kF is the point beyond which that kind of scattering becomes energetically costly. Right. Yeah. Sorry, yeah, I should have. This is kF. Sorry. Okay. All right. I think what is this supposed to be the time? 10 more minutes? Ah, okay. Yeah, actually, I went a little bit faster than I thought. Let me see. Okay, I can start talking about a different thing. I think 10 minutes is okay for that. But before I leave this subject completely, is there any more question about this quantum Hall stuff? Right. So yeah, let me make the comment that this is a case where the duality is not directly useful for the CFT per se, because the underlying CFT is just a free Dirac fermion. I mean, we don't need another fancy tool for studying just free Dirac fermion. But once we perturb away from the fixed point, let's say using a magnetic field, the question actually turn out to be much harder than just the free fermion, and this is where this duality becomes really useful. Yes. what's due to Landau what? Oh, no, those are non-universal features that, sorry, what do you mean by what's dual to that? You mean the original Landau level interaction? No, I don't, it's some complicated relation that nobody has figured out. I don't think anyone has a good scheme to calculate the Landau parameters just starting from the microscopic interactions in the Landau level. No, the thing is, these fermions are coupled to a U1 gauge field. Exactly what happens with those is not completely clear, actually. Yeah, they look exactly marginal only for short-range interactions between the fermions, but the gauge field mediates some long-range interaction, and that has to be re-examined. It's a pretty complicated sort of problem. Yeah, but there is some requirement on the Landau interactions if the fixed point is a Fermi liquid like. So I'll just leave it there. All right. So let me talk about another way to view the SL2Z operations I talked about in the previous lecture. So we're done with the application, at least for now, of these dualities. And let me give you a much more transparent, at least from some angle, origin of this SL2Z relations. The idea is that let's think about the boson vortex duality. Let's go back to the very simple thing. But now let me decide to view that as the boundary of a 3+1 dimensional bulk, right? And further, I decide to, previously I had my Wilson-Fisher bosons coupled to a U1 probe U1 gauge field. Now let me do something slightly different. Let me declare that this U1 gauge field is not a probe gauge field, it's a dynamical gauge field, but it's dynamical not just on 2+1D space-time, but it's actually dynamical in the whole 3+1 dimensional bulk. Right? So it basically becomes a 3+1 dimensional U1 gauge theory. Okay? Even though I still require my my Wilson-Fisher bosons to only live on the boundary. Okay? So why do I do that? Well, the reason to do that is because when I write down the dual theory, remember the dual theory is formulated in terms of a dual boson, phi tilde, that looks like, well, it is the vortex corresponding to this phi boson. And this phi boson is nothing but the gauge charge of this U1 gauge field, right? So from the 3+1D bulk point of view, you can ask what corresponds to a vortex on the boundary, right? You can say, okay, in the 3+1 dimensional bulk, a gauge charge will correspond to a charge on the boundary. Well, the charge can be gapped in the bulk, can be infinitely gapped if you want. But on the boundary, it corresponds to this charged Wilson-Fisher boson. So now here, I want something that corresponds to a vortex on the boundary of this gauge theory. What does that? Well, the answer is it's a monopole. Right? I have a 3+1D compact U1 gauge theory the naturally gapped excitations are the charge and the monopole, right? And I can make this more precise by imagine I have this U1 gauge field, you know, in the entire space, and then I drag a monopole from the vacuum into the into my bulk, and on this surface, I will leave behind a vortex. Right, so that's how the bulk monopole corresponds to the vortex on the surface. So monopole in the bulk gives me vortex on so bulk. Two plus 1D. So this strongly suggests that the boson vortex duality I was talking about is really the surface manifestation of the bulk electric magnetic duality, right? It's the statement really that I can formulate my bulk U1 gauge theory either as a U1 gauge field coupled to charge, or the dual U1 gauge field coupled to the monopole. So let me remind you for a U1 Maxwell theory. In 3 plus 1D, right? The theory is essentially invariant. If I switch the EM, the electric and magnetic field, essentially I rotate my electric magnetic field by 90 degrees, right? If I decide, suddenly I just decide to call my electric charge magnetic monopoles and magnetic monopole electric charge, the theory looks fine. It's just another U1 gauge theory. Right? My coupling constant may change if you treat the theory more carefully. In fact, E squared goes to 1 over E squared in the Maxwell theory, but otherwise the theory looks the same. Right? And the important thing is the charge gets exchanged. So this is extended if I treat the gauge theory more completely to an SL2Z structure. Right. So more generally, so this is for pure Maxwell. So more generally, I can think about the Maxwell theory and the theta term. Right. This is the general U1 gauge theory, how I write a general pure U1 gauge theory in 3 plus 1 dimension. And when I have the theta term in a U1 gauge theory, well, it's a total derivative, so dynamically it doesn't really do anything. It doesn't change my propagator or anything. What it does change is to change the spectrum of my excitation. Right? Imagine having gapped excitations that are charge and monopole. And then what happens is that if I have a monopole here, that formally gives me some integral of divergence of B. That's some 2 pi times integer, right? So that's how I define my monopole. This term will assign an electric charge to the monopole. So this, let's say if this is the magnetic charge Q is sorry, Qm is n, then the electric charge will be theta over 2 pi times n. Okay, so that's what the theta term does. Okay. This means that if I now count what type of excitation I have, there is something called the charge monopole lattice. Essentially, I can think about my magnetic charge, Qm, which are quantized in integers. And then I can talk about my electric charge, Qe. Well, they are integers, except if my particle also carries magnetic charge, the Qe will shift by that amount. So in general, it will look something like, so on this zero magnetic charge line, it's still integer, but then on this line, it will be shifted. It will look something like that. So you basically get a lattice, a 2D lattice. And the rule of thumb is whenever you get a 2D lattice, you can think about modular transformation. It's a transformation that essentially relabels your lattice points. So essentially what you can do now, let me see how much I can do. Yeah, I think okay. Let me see. Yeah, I think I'll just pause here because I've introduced the charge monopole lattice, and I'm gonna do something starting from tomorrow on this. And yeah, let me just pause here for today. Okay. Yeah, the content tomorrow is going to show you that doing modular transform on this lattice is essentially the SNT modular transform on the boundary that generates the duality.
All right, any question? All right, otherwise we're gonna go for lunch, and we resume again at 3 p.m. for Anders lectures.